So next, let's return to our fourth property of a conductor in electrostatic equilibrium. As a quick reminder, the first three properties were that the electric field was zero everywhere inside a conductor in electrostatic equilibrium. A conductor in electrostatic equilibrium has all of the excess charge on its surface or surfaces, and the magnitude of the electric field is the charge density divided by epsilon naught. It's always perpendicular to the surface, points out of a positive and into a negative. Those were the first three properties. Now we're going to come to the fourth property that says that the charge density, that's sigma, charge over area, that's bigger where the curve is steeper. So let's think about how we're going to solve this. Let's imagine we have two conductors and they're connected by a thin conducting wire. So the whole thing is a conductor. Conductor, conductor, conductor. Our first sphere has a radius that we'll call R1. It carries a net charge Q1. Our second sphere has a radius we'll call R2, and it has a charge we'll call Q2. R1 is smaller. It has a steeper curve than sphere 2. So this one is a steep curve, and this one is a more shallow curve. So where we say something like the curve is steeper, it means the radius of curvature is smaller. R1 less than R2. Okay, so there's our setup. Now let's think about what we've said about, what we've established about potential. Entire conducting surfaces are at equal potentials. So the potential here is the same as here, is the same as here. So we know that the potential of sphere 1 is equal to the potential of sphere 2 and is equal to the potential of the wire while we're at it. Okay, what's the equation for the potential at the surface of each of our two spheres? At surface, K times Q1 over R1 equals K times Q2 over R2. So the potential at the surface here is equal to the potential at the surface here because the potentials are the same everywhere. We've got K on both sides, so we can go ahead and divide through by K. And let's ask, is there anything we can do about Q1 and Q2? Can we figure something out here? Well, I know that sigma 1, the surface area charge density, is Q1 divided by area 1. Area means the surface area of the sphere, so Q1 divided by 4 times pi times R1 squared. Likewise for sphere 2, sigma 2 equals Q2 over area 2 equals Q2 over 4 pi R2 squared. I can rearrange this equation and solve for Q1. Q1 equals sigma 1 times 4 pi R1 squared. I can rearrange this equation for Q2. Q2 is sigma 2 times 4 times pi times R2 squared. Let's put Q1 and Q2 in this equation over here. Sigma 1 times 4 times pi times R1 squared divided by R1 equals sigma 2 times 4 times pi times R2 squared divided by R2. Let's do a little simplification next. Let's divide both sides by 4, divide both sides by pi. I've got R1 squared on top, R1 on bottom. R1 goes into R1 squared, leaving R1 behind, likewise on this side. Okay, let's write my equation down again. Sigma 1 times R1 equals sigma 2 times R2. I was trying to sort out the relationship between the charge densities, so I think I'm going to divide my R1 to the other side. Sigma 1 equals sigma 2 times R2 divided by R1. R2, remember, is big. R1 is small. So a big number divided by a small number will be greater than 1. So our result is that sigma 1, the charge density on our steep curved sphere, is bigger than sigma 2, the charge density on our shallow curved sphere. Okay, so that tells us about the charge density. What else might we take away from that? Well, let's remember our third property, the electric field is equal to sigma over epsilon naught perpendicular to the surface out of a positive into a negative. So we'll say out in just for shorthand to remember that. Sigma depends on the radius of curvature. A steep curve has a small radius of curvature and a big charge density. Therefore, it would have a big electric field. So if we have a steep curve, and another way to describe an object with a steep curve is we might call it pointy, it has a big electric field. Okay, and this is a measurable effect. We can certainly find that. There is kind of a neat application of this. I'm just going to see if I can bring this up on my laptop and will my iPad capture it. And a good application of this is actually lightning rods. Turn my volume up on my computer, move the iPad. A little bit of light, hopefully this is not too bad. Unplug the headset. So for our video, I'll just hit play. The audio is not too important. So our application is going to be lightning rods. This is a video of a thunderstorm at the CN Tower in Toronto. And the old adage is that lightning never strikes twice. That is definitely untrue. So that's just some audio of some kids watching the lightning. In this video, the lightning actually struck the CN Tower over 40 times during one single storm. So why did that happen and how were the people safe? The application of what we just showed is a lightning rod. So a lightning rod is a thin, pointy piece of metal that just sticks up off the top of your building. If you're from a place that has a lot of thunderstorms, you probably have a lightning rod on your home. So because the lightning rod is pointy and it sticks up, it attracts the lightning out of the sky. And the lightning will hit the lightning rod, the steep pointy thing, instead of hitting the surroundings with the more shallow curves. So then the people inside get to be safe because the energy is safely distributed down through the building, through the lightning rod into the ground. And this is why, maybe if you're outside in a thunderstorm and lightning is starting to strike your area, you know that you shouldn't be the tall, pointy thing. So if you're in a field, you should lie down flat on a grass, if there's lightning strikes right next to you. It's why you shouldn't hide under a tree because the tree is the tall, pointy thing and you don't want it to come too close to you. Okay, so there's our application in lightning rods, which is pretty cool.